Okay, it's a minute past the hour, so we can get started. So hello and welcome everybody. My name is John Perkins, and thanks for tuning in to the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program at the USGS and is co-organized with Shelby Arendt and Jamie Kostelnik. For those of you who are new to the meeting, you have the ability to submit questions either through the chat window, or you can use the raise your hand feature in combination with your microphone or video camera. And we typically wait till the end of the presentation to take questions. And in the meantime, please do your best to make sure that your microphone is muted when you aren't intending to speak. So today it is my pleasure to introduce Jan Blahut, who is here in the US as a Fulbright visiting scholar with the USGS investigating thermal-induced stress in rock masses in Yosemite National Park, together with Brian Collins here at the USGS at Moffett Field and Greg Stock, the park geologist at Yosemite. Jan got his master's degree in physical geography at Charles University in Prague, Czechia, and went on to get his PhD in environmental sciences at the University of Milano, Bicocca, Italy. And Jan presently works at the Institute of Rock Structure and Mechanics at the Czech Academy of Sciences, where he deals primarily with rock slope stability and the influence of temperature, which we'll be talking about today. So yeah, take it away, Jan.
Okay, thank you, John, for inviting me here for the seminar. Thank you for having me here. First of all, I would like to thank all my colleagues that helped me with the research I will be presenting today. And my topic is basically the influence of temperature on the rock. I prepared 3 case studies that I would like to present. The first one is to show what heated rock can tell us. The second one is the effect of wildfires on rocks, that particularly one wildfire that happened 2 years ago in Czech Republic. And the third one is a study I'm doing here in Yosemite Valley about the long-term effect of insolation or temperatures on the rocks and on thermal stress, basically. So let me start. Basically, with the basic theory, what are the effect of the diurnal and annual air temperature changes on rocks? The first one that is quite obvious is the thermal expansion and contraction that happens because of the volumetric change. When the rock is heated, then there is the influence of exfoliation. During winter, there are the freeze-thaw cycles or the action of frost. Then there is also a thermal gradual disintegration of the different minerals. For example, quartz is quite prone to that because the largest volumetric change compared to other minerals. And of course, when we have higher temperatures, you have more temperature-induced chemical weathering of the rock. I will now show you a case study that is from within Czech Republic, very close to Prague. We have a monitoring site in a former quarry, granodiorite quarry, and the pros of this we call it natural laboratory is that we are basically allowed to do anything there because it's not a protected area. And we do temperature monitoring of the rock wall and also inside the rock down to 3 meters. We have a meteorological station on the rock. We also monitor the surface stress with foil tensometers and the crack dilatation with crack meters. And what we performed here was a 24-hour time-lapse measurement using a thermal camera to be able to capture the differences on the rock face. The rock is quite small, actually. It's about 8 meters high and about 20 meters wide. And we didn't expect at first that we will capture such a big differences, because on the surface the rock looks very similar except for some cracks. What is the theory behind the study is that, of course, we received a heat flux during the warm part of the day that accumulates in the rock, and then during the night, we actually, or during the cooler cooling time, we actually capture the heat flow escaping the rock. For that, we used a thermal camera, and we have made thermal images every 10 minutes. And then these were post-processed in a laboratory. You can see in the video how the rock is being heated during the warmer part of the day, and after that it started to cool down. And you can even see now the differences in different parts of the rock, not only caused by the presence of cracks or joints, but even in like places that where you wouldn't expect it that look the same. By analyzing the data, we were able to distinguish 3 zones. Here they are called A, B, and C, and that they behave really differently. Here is the graph that is called, or we calculated an index called cooling rate index. That is basically a speed of cooling per minute, a decrease of temperature per minute. And you can see in blue, you can see the air temperature, while in the red, yellow, and green, there are these 3 places called regions of interest, A, B, and C, that behave differently. We didn't expect that at the beginning, and we then, based on this differences, we extracted rock cores on this rock wall, and we were able to see quite big difference in the properties of within these 3 sites that are separated by, I don't know, 2-3 meters basically. And you can see that the place called A, that is in the left bottom part of the rock, we extracted basically unweathered rock core with very low porosity, 0.9, and very high P and S wave speeds, and consequently the dynamic elastic module. On the place B, that behave differently from the place A, even though on the first side they were looking quite similar. It had almost twice the porosity and was moderately weathered, and the place C was highly weathered, with porosity reaching almost 4%, and with much lower speeds of P and S waves. And we are able to do some regression analysis between the samples and the cooling rate index that shows some dependence on the rock properties with the cooling rate index. So the purpose of this study, or the results of this study, was that basically using the infrared thermography, we could distinguish the different properties, and we could relate them to with a regression analysis with the speed of cooling, basically. We also realized the best time to perform this kind of analysis was during a warm summer day, during the cooling phase of the warm summer day, when the rock is most heated, because then the data are better distinguishable, the results. But of course, to make some general results or general relationships, we need further test on other sites as well. So this is our approach, how what a heated rock can tell us using infrared thermography. Now I will show you what heat can do to the rock. Basically, during or after a wildfire, 2 years ago, or 2.5 years ago, we experienced the largest wildfire in Czech Republic ever recorded. It affected an area of a national park called Bohemian Switzerland, next to the German border, which is famous for its Cretaceous sandstone formations. It has the largest sandstone rock arch in Europe. It's about 26 meter wide, which is, of course, nothing compared to places like Archies National Park, but we are quite proud of it. And it's an area of, I would say, great geomorphological value with a lot of valleys and canyons. And this area has been struck by the wildfire in July and August 2022. It was as I said, it was the largest wildfire, but and it reached around 10 square kilometers of burned area, which is kind of funny compared to Californian wildfires. But it affected a large portion of the territory. But the effect of the wildfire varied a lot depending on in different places. I must say it was accelerated in places where there were dead spruce forest, because few years ago we had a invasion of a bark beetle that caused death of large portion of the spruce forest in the area, and in that places the fire was very severe. But as you can see on this figure, on this map, most of the area that was affected by the wildfire was with a low or even unburned classification or class, and only like 2% of the area was highly burned. The general effect of wildfire on a rock mass is known that during a wildfire itself, there is some thermal cracking occurring that can result in direct rock falling. And after the wildfire, on a more local scale, we can see a lot of spalling. And this spalling is occurring up to a few years after the wildfire. And then a new rock surface or new rock crust develops, and it hardens the rock. So this is the theory. What we have observed in the area was a lot of spalling from few millimeters to few centimeters, but we have seen very limited rock falls. Actually, we have made some survey regarding this, and most of the rock falls that occurred during or after the wildfire were in areas that they were already, or the fallen blocks were already in unstable positions before the wildfire. What we have done during this study for the national park, we extracted rock cores from the affected rock masses and boulders in 3 sites. They are called A, B, and C. The A site was in a valley that was highly affected by the wildfire, while the B area was moderately affected, and the C area was some sort of control area that served that wasn't affected by the fire at all, and was used as a controlling samples to compare with the results from the other areas. What was the first thing we noticed is that we drilled about almost 50 cores with a 100 millimeter diameter, but we were able to use only 37 of them because some part already disintegrated during or after the drilling. So we already found during the drilling phase, we found that there is a big variability within the sandstone layers itself. Also, we had to restore, because we were in national park, we had to restore the area to original conditions, which was kind of funny because we were supposed to use concrete mixture with sand to cover the holes, but the spalling was not yet stopped. So we were telling the officers from the park that probably what will happen in several years, that we will have concrete visible on the rock itself, while the rest of the rock will erode. But we will see what will happen. Okay, so what was our approach for the sample analysis? As I told you, we extracted 10 centimeter pores, and first of all, we analyzed the speed of the P waves and its change in the depth. So we measured the P wave velocity next to the surface, and then about every 2 centimeters in the direction inside the rock. After that, we decided to redrill the rock core and to get 3 samples, to get a Brazilian sample, which is a disc of 50 millimeter diameter and 30 millimeter high next to the surface, then a sample for USGS testing, for compressive strength testing, and then another Brazilian specimen. Why we did that? It was because we have observed quite big differences in the P wave velocity with the depth, the changes of the velocities with the depth. So in the area that was highly affected, which was the area A, we can see a clear trend of increasing P wave velocities with the depth. That means we get stronger rock going more in depth to the rock. In the moderately affected area, which was the area B, we don't see such a strong trend. And in the control area here, we didn't see these changes at all. So this actually showed us that the wildfire might have some influence on the rock directly in the first few centimeters. And because of that, we decided to split the core into the Brazilian specimen next to the surface, then the USGS specimen in the middle, and the non-affected specimen in Brazilian specimen in the bottom. And we then analyzed these red-drilled specimens again using P and S waves and some basic characteristics like bulk density, porosity, and so on. And here are the results for the USGS samples, and they didn't show any clear trend or clear change with within the or between the different areas, the highly affected area A, the moderately affected area B, or the non-affected area C. And this was probably caused because the effect of the wildfire was limited to the first few centimeters of the rock near the surface. We also observed a bit of problems when we were actually doing the mechanical tests on the rocks, because sometimes the samples were so disrupted and so highly porous, reaching like porosity of 20%, that we were unable to prepare the samples properly with clean surfaces, and this caused problems during measuring the uniaxial compressive strength. As you can see on the on these figures to the right, where the sample behaved strangely in a non-linear way. And this was probably caused by the uneven closing of the pores and microcracks in the sample. So actually the mechanical testing wasn't really able to give us so many results as the P and S waves measurements that we used for calculating the dynamic elastic modeling. On the contrary, the analysis of the Brazilian samples showed us some nicer results. Here you can see again the samples from the three areas called A, B, and C. And when it's in the more vivid color, it's from the surface. It's called Brazil 1, Brazil 1, yeah. And if it's from the inside the rock, from the depth, it's called Brazil 2. It's the less vivid color. And you can already see the differences within the particular sites. If I look at, for example, at the P waves, for example, or S waves, you can see much lower speed of P and S waves near the surface of the wildfire affected samples than inside the rock. And this difference is not seen, we were not able to see this difference in the non-affected area. There was almost no difference between the surface and the inner part of the rock in the non-affected area. What we also observed here was that in the wildfire affected area, the variability of the results was much smaller at the surface than inside the rock, which suggests that the wildfire caused some sort of unification of the properties next to the surface of the layers. The same results were observed during the tensile strength testing. We have seen some differences between the fire affected and non-affected sites, and we have seen very low difference in the samples from the area where there was no fire. So to sum up this study, we showed that the wildfire had a significant influence down to, let's say, 5 centimeters, 3-4 centimeters maximum. We didn't notice any dependence of the changes on the porosity or density on the samples. But what we found was that there is very large variability between the different sandstone layers we sampled. And this variability was already there before the wildfire. And actually the wildfire caused some sort of unification of the surfaces that were exposed to it. Also, there was a big variability within the fire itself, because in places where there was a tree that fell down and was touching directly the rock face, we observed much more spalling than in other areas, obviously. We also have seen that using ultrasound measurements of P and S waves can give us better results than the mechanical testing that, especially with highly porous samples that were already disturbed by the wildfire, we weren't able to extract nice results from that. Yeah, so that is basically what we have found, the effect of the wildfire on the rock. And now I will show you the last case study that is focused on the long-term effect of insulation on the rocks. So what we are doing now in Yosemite Valley is that we are monitoring temperature in 2 boreholes on 2 sites, not far away one from each other. And we can say that the motivation was what can be found already in a almost 100-year-old book of geological history of Yosemite Valley, where Mathis noted that there is a big mechanical effect of sun or radiant heat of sun in exposed areas, as you can read in the red boxes. To observe this, we installed 2 boreholes. One is southwest facing next to the Big Oak Flat Road, and the other one is northwest facing next to the Wawona Tunnel. And in each borehole there are 11 thermocouples measuring temperature every 10 minutes. One is on the surface, one is at 5, 10, 20, 30, 50, 75, 100, 150, 200, and 300 centimeters at depth. And the measurement started in the second half of April. And here they are. Here there is the temperature oscillation at the south-facing Cascade sites in red and the surface, and on the north-facing Wawona site in blue. In the bold there is the 24-hour moving average, and in yellow you can see the temperature measurements from the 3 meters depth from the Cascade site, and from the Wawona site is in green. I noticed that I have here it should be Wawona. In green it should be Wawona, not Cascade. So you can see already that there are big differences between the 2 sites, even in the amplitude or in the absolute temperature. When we compare the 2 sites, you can notice the big differences in the south-facing side, where the average temperature on the surface from May to December was almost 27 degrees, with a temperature range of 55 degrees almost, and a maximum of 56 degrees on the surface. While on the Wawona side, the north-facing one, the temperature range on the surface was only 30 degrees, with an average of 16 and a maximum of 32 degrees in summer. You can also see that the temperature at the 3 meters is about 10 centimeters higher, 10 degrees higher in the south-facing slope than in the north-facing slope. But obviously you can, of course, notice these differences also within one rock block. I have an example here from under El Capitan, from the under the North America wall. There's a granite block with a diorite enclave, and we can, even in a winter day on 15 January, 2 weeks ago, there was a noticeable difference of more than 10 degrees within few centimeters. And of course, this is causing a lot of stress on the rock, these differences. When I go back to the results of the borehole measurements, you can see the average daily amplitudes at different depths on this figure. And you can see in the south-facing slope that this amplitude is reaching almost 25 degrees daily on average on the surface, while only 5 degrees in the north-facing slope. And these daily oscillations are noticeable or visible down to 1 meter, like almost every day. When we compared I compared the surface temperatures and the air temperature of the nearby station that is located at the Turtleback Dome. You can see that the air temperature coincides quite well with the north-facing slope, but it's much lower than the south-facing slope. And this suggests that when assessing the influence of high temperatures on the rock triggering, for example, we have to take this into account, because normally we are limited usually to use only air temperature as an information, but we have to take into account that the rock can be heated, I don't know, twice as much if it's south-facing. Here are, on this graph, there are average daily temperatures and amplitudes. And you can see, as I showed before, that the amplitude and the average temperature in the north-facing slope is actually very close to the air temperature. But on the south-facing slope, the amplitude is almost 4 times higher than in the north-facing slope, and the average temperature is also much higher. When we compared the hottest and coldest days using the highest air temperature measured, that was on 6th of July, you can see that the amplitude measured at the south-facing slope during one day was about 24 degrees, while the air temperature was only 8 degrees amplitude. And in the coldest day, it was the same. We got a mean temperature of minus half degree centigrade with an amplitude of 3 and 3.3 degrees for the air temperature. But on the south-facing slope, we observed the mean temperature of almost 11 degrees and an amplitude of 13 degrees. And this obviously should have an effect, a long-term effect on the rock. When analyzing the monthly temperature range at the surface, we can see that on this graph that in the south-facing Cascade side, we have a maximum range of almost 44 degrees centigrade in October, and this high range is usually the highest ranges are in October, November, and December, and we expect to have it also in February in the spring or end of winter. While on the north-facing slope, the highest temperature range was in May, and then at the end of summer in August, September, and October. When we look at the daily temperature ranges at the surface, we see very similar results. We have maximum range on the south-facing slope in November, but also the minimum. But you can see from the graph that the oscillations or temperature variability is mostly is highest during the fall and winter months. While on the north-facing slope is the contrary. We have quite stable variations during fall and winter, and we have the highest temperature variability during August, late summer. If you look at the average monthly temperatures by depth, on the two sides. On the left side, we have the south-facing slope, Cascade side. On the right graph, we have the north-facing slope at the Vavona side. You can see the, let's say, similar pattern, but shifted by about 10 degrees as the south-facing side is about 10 degrees warmer than the north-facing one. What you can notice here is that when the curve of the graph is going to the right side, it means that we are in the warming period, and if it's going to the left side, we are in the cooling period. So now we are actually in the cooling period, but we don't have the whole year record yet. This will we have in May. I also try to extrapolate the temperature amplitude to the depth to calculate the depth of the stable temperature. Of course, this is not scientifically valid yet because we don't have the whole year record. But now the extrapolation, the exponential fit shows that in the south-facing slope, the stable temperature is about at 6 meters, and in the Vavona, it's more than 7 meters. This coincides with the other sites we monitor in Czech Republic or in Italy, where we have usually the stable temperature at around 8 meters. And but to confirm this, it will certainly change when we have the whole year record. So from this, you can see that the thermal behavior on just 1 kilometer apart or 1.5 kilometer apart on the other side of the valley is completely different. So we then looked at the borehole cores we extracted. They are both El Capitan granite. They will both boreholes were without any cracks or joints, and the rock cores were are macroscopically very similar. Only in the north-facing Vavona side, we have a dike. We drilled a dike at the depth of 1.8, between 1.8 and 2.3 meters depth, with a diorite enclave afterwards. And we use these cores for further analysis to compare the properties of these sites. In red, you can see the results from the cascades from the south-facing side, and in the in blue you can see the results of the cores from the analysis of the cores from the north-facing Vavona side. On the x-axis, on the horizontal axis, you have the depth of the sample that has been analyzed, and on the vertical axis, you have the corresponding properties. So the bulk density doesn't differ a lot, but there is the samples from the south-facing slope from cascades are a little bit have a little bit higher density than the north-facing slope. Also, I forgot to mention that in gray, we have the results from the part of the dike and the diorite that we didn't use in the analysis because this is a different material. In terms of porosity, you can see that there is a back to the I have to mention about the bulk density that we don't see any big changes in the bulk density with the depth. While when we look at the porosity, we can see a clear trend on both sides, then where the porosity is decreasing with the depth. While when we measure the P and S wave velocities, we got actually nice results here. And you can see that the samples the cores from the cascades from the south-facing side have quite different trend from the north-facing side. The change with the depth especially of the P wave velocities is much faster in case of Vevona, north-facing side, than the cascade side. And this suggests that the rock at the north-facing slope is actually less weathered and than the south-facing slope, and also that the south-facing slope, the weathering is very more similar in the surface and in the 3 meters, while in the north-facing slope, the weathering at the surface it's much higher than inside in the 3 meters. When we compare, when we calculated the dynamic elastic moduli, we obviously used the P and S waves velocity, so the trends were quite similar. You can see here the results for the Young modulus and Bolt modulus. Again, you can see much faster change in Vevona side, north-facing side, than in Cascades. You can see the same for the shear modulus as well. So this suggests actually that the Vevona side shows a stronger gradient of change, and with much lower temperature oscillations, while the Cascade side shows much lower dynamic moduli and lower P and S wave velocities than the north-facing side. And we hypothesize that these are caused by the diurnal and annual thermal stress changes that affect the rock, and that the influence of these temperatures are actually, or the influence of the temperatures actually higher than influence of other factors as groundwater, because we didn't see any cracks or joints where the groundwater can flow. Obviously, we need some more measurements to from multiple locations to prove this, confirm this hypothesis. But I think the results are quite interesting. So that would be all from my side, and thank you very much for your attention.